So we're going to start this lesson by looking back at the intro activity to trig. I filled in all of the values for these three columns. Got a little messy there in the middle, sorry. But my average values worked out to be for opposite over adjacent, 0.5685, for adjacent over hypotenuse, 0.8738, and for opposite over hypotenuse, I got 0.4967. Okay, these are pretty good, but they're not exact numbers, and there's some error in my measuring, and maybe you got slightly different numbers when you measured your triangles, but hopefully we got all the same kind of ratios divided out here. I might have put something in my calculator, averages here at the bottom, just kind of hopefully figure out what's going on. So why did we do this? Why did we do all this division? Well, because turns out when we have similar triangles, right, if we think about what similarity means, every angle size, every unique angle size is going to create very specific conditions for side lengths, right? If we think about all those 8 similar triangles that we use to measure these, when we did these divisions here, we got really close to the same numbers, right? It turns out when you take the opposite and divide by the adjacent for any triangle, any right angle triangle with a 30-degree angle, you get about 0.56, right? You get about 0.56 or 0.57. So it doesn't matter how big the triangle is, you get this ratio. When you take the adjacent and divide by the hypotenuse for a 30-degree angle in a right angle triangle, you get about 0.87 as a ratio of those side lengths. And when you take the opposite and divide by the hypotenuse, you get about 0.5 for a 30-degree angle. Now, if we were in the classroom and somebody had a 50-degree angle and a 60-degree angle, the ratios would be different for different angles, but the ratios would be the same for all of their similar triangles. So what's really cool now is we don't have to worry about similarity anymore. Now we can just kind of start calling these things by their ratio name. So we have these 3 primary trig ratios, and the opposite over the adjacent, we call it tan, and the adjacent over the hypotenuse, we call that cosine, and for the opposite over the hypotenuse, we call that sine. So we don't even have to, we don't have to go around saying, oh, the ratio of the opposite over the hypotenuse for a 30-degree angle is about 0.8. The degree angle is 0.87, okay? And what's really cool is, in our calculator, if I press, I'm going to zoom in a little bit on my calculator here. As long as my calculator is in degree mode, and you'll notice I have a little D up here in the display, you might have a DEG in the display. That means you're in degree mode. That's good because our angles are measured in degrees. If you're in radian mode, you'd have a little R or a little RAD in the display here. We'll use those in grade 12. We don't need to worry about those right now. And if you are in gradient mode and has a little G or GRAD, like it says grad in the display of your calculator, you are either in, 18th century, 19th century France, under Napoleon's rule where he tried to make everything out of 100, or you're working as a surveyor in a geological study, because nobody else uses gradients. So what you want to do is you want to figure out what button is going to move you back into degrees. And I have a couple ways to do that on my Casio. I can press shift mode. And then I can say, oh, I want to be in degree mode. That's 3. and it changed me back to degree mode. Or what possibly lots of you guys are going to have is like DRG with an arrow down here. I'll point to it with my fingers. You can't see it with a black pen. DRG with a little arrow here, and I just press Shift DRG. Nope, that's not going to do it. That's going to change it into something else. Okay, so for me, for my Casio, I'm going to use Shift mode, and then I'm going to change it that way. But I know if you have a Sharp, that DRG often works, kind of maybe somewhere around here. Okay, so I'm in degree mode. Perfect. You need to always be in degree mode. Always, 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 or I'm going to get everything wrong. All right, so let's take a look. If tan of 30, if I put tan of 30, tan 30 in my calculator. And now again, this is where you're going to want to know how your calculator works, because some of you guys are going to have to press 30 and then tan. I think that's the way some Sharps work, and I have no idea how Texas Instruments work. I don't know. But for my Casio, I know that I have this nice double display Casio here, so I can see tan 30, and then I press equals. And oh my goodness, look at that. It's 0.5773, which is really close to the values that I got. That's really, really close. So, you know, my measurement isn't very exact. So, but we got really, 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 really close. We got the, you know, down to the hundredths place correct. That's fantastic. All right, so let's take a look at cos of 30 degrees. I hope you're kind of already guessing what cos of 30 degrees should be. Look at that. It's 0.8660. We got, you know, ballpark. We got 0.8738. It's pretty good. Again, you know, if you round this, we've got to the hundredths place correct. So yeah, so 30-degree angles, no matter what triangle they're in, as long as they're in a right angle triangle, are going to give us this constant ratio here. And then last but not least, sine of 30 degrees is 0.5. And we actually got 0.5 exactly twice on our chart here, and really, 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 really close otherwise. So these are the exact values. Your calculator is going to have the exact values. If you take grade 12 pre-cal, you'll have to memorize that sine 30 is 0.5, but I'll show you how to do that later, so don't worry about that. But what I did want you to see in this is how these ratios can be used to describe all these angle sizes. And every angle size has its own ratio. Sine of 60 is, oh, well, that's very interesting. It's the same as the cos of 30. And I'm going to let you figure out why that makes sense. But we'll do that after. Okay, so every single angle has its own ratio, and we need to know those three ratios. So these are the notes we're going to work off of today. Our three ratios are tan theta, cos theta, and sine theta. Remember, we use theta to represent unknown angles, and anytime we use one of these trig ratios, we need to make sure that we have an angle size here, whether we call it angle A or whether we call it angle theta, whatever. We never just say tan equals, because tan doesn't equal anything, but tan of an angle has a value, so that's what we want to consider. Okay, so tan theta is our opposite over our adjacent. Cos theta is our adjacent over our hypotenuse. And sine theta is the opposite over our hypotenuse. Okay, and then just tan isn't the whole word. Tan is short for tangent. Okay, cos is short for cosine, and sine, I know lots of students call this sin. I hear sin theta so often, especially in 10. It's just not correct. We don't call it sin, we call it sine, and it just sounds a little bit like you have no idea what you're talking about if you call it sin. So we want to make sure we use the right word for this. This is sine, because you would not believe this is a shortcut for the crazy long word sine. It's so ridiculous, but nonetheless, that's the way it is. So it seems like a lot to try to remember, but it's not, because I've got a handy little shortcut for you that anyone who has ever learned trig can tell you this shortcut. And the shortcut is SOHCAHTOA. Okay, so if you have an older brother or sister at home, or maybe your parents might even remember this, it's kind of like knowing bedmass. You know how everyone knows bedmass? Everyone who's learned trig knows SOHCAHTOA. It's just a quick, easy thing to remember. It's so easy, in fact, that some people think, oh, whatever, it's no big deal, and they never bother actually kind of learning it. So what I would do is I would write it out a couple of times. I would just like literally take a piece of scrap paper and write SOHCAHTOA a couple of times. And then, because all of a sudden you don't want to be writing, I don't know, SOHCAHTOA, and then you have no idea, like you're trying to do a question and you're like, what is this thing? Okay, so SOHCAHTOA, the way it works is sine is our opposite over our hypotenuse, and cosine is our adjacent over our hypotenuse, and TOA is our tan, our tangent is our opposite over our adjacent. Okay, so if you can remember SOHCAHTOA, then you will remember these ratios, and you don't have to memorize them as this set of words here. Okay, because I don't normally like shortcuts in our learning. I like when we fully understand stuff, but SOHCAHTOA is just kind of one of those things you have to memorize, because there's no way to like stop and remember that sine means opposite over hypotenuse. It's just something you have to know. Okay, so how do we use this? Well, I'm going to give you an example up here. So if I give you a right angle triangle, and let's just say this side is 12 meters and this side is 15 meters and the hypotenuse is 19 meters, and I'm going to call this guy theta here. Okay, so just triangle, right angle triangle with 3 sides label. And remember too that we can only use these ratios for 90-degree angles, or 90-degree triangles, right? Right triangles, they only work for that. So how do we write this? How can we set this up? Well, we can say tan theta is our opposite over our adjacent. Okay, so we can do a shortcut like that. I would strongly recommend you don't use O over A. This is kind of the shortest that we typically write these things. And tan theta then is going to be our opposite, which is 15, divided by our adjacent, which is 12. Okay, and all we're doing here is just writing out the ratio. I'm not doing anything with it yet. We'll get there, but right now we're just writing out the ratio. So how would we write our cosine ratio? Well, cos of theta is the adjacent over the hypotenuse. And so our cosine ratio for theta, our adjacent is 12, and our hypotenuse is 19. And then finally, sine theta, which for some reason, I have no idea why I ended up having a favorite trig ratio, but I really like sine. It's the weirdest thing to have a favorite trig ratio, but I do, and sine is my favorite. So it's the opposite over the hypotenuse. And the opposite to angle theta is 15, and our hypotenuse is 19. So sine theta is 15 over 19. And that's how we would write our 3 primary trig ratios for this particular triangle. And later on, I'll show you how we can figure out how big theta is using these trig ratios. And we can solve for other side lengths and all that kind of stuff. But for now, we just want to know about these ratios. Okay, Final question on the notes page. What's the connection between the primary trig ratios and similar triangles? Like, why can we use these ratios to solve problems? Well, each angle size, and like, I don't even mean whole numbers like 30 degrees or 40 degrees. I mean like 30.00001 has its own ratio for cos and for sine and for tangent. So every single angle size creates its own unique set of ratios. And all of those ratios are stored in your calculator. It used to be once upon a time, you used to have to look these things up in a table. I had to do that in math class. Not because we didn't have calculators. I'm not that old. It's just my teachers, we weren't allowed to use calculators for anything in class. Nowadays, we want really, really exact answers. So your calculator has these ratios stored to a lot of decimal places. So we're going to get really accurate answers. But yeah, they're stored there, so we don't have to worry about looking them up, thankfully, or memorizing them until we get to grade 12. So I hope that makes sense, and I hope you can see the connection between sine, cosine, and tangent, and the work that we did with these ratios in the last lesson. Okay, so try your independent practice and let me know how it's going.